Thank you, Professor Blanco, for the introduction and for the invitation to speak here today. It's a pleasure to be here and to see all of the presentations. It's been very interesting, so thank you very much. As Manuel said, my name is Jeff Cumpston. I work at RWTH Aachen University in the chair of Process Systems Engineering there, and I'm going to present to you today, if I can get that up on the screen, excuse me. A formulation for robust optimization of aiming strategies of heliostats and solar power tower plants. Excuse me, the title's reversed there a bit. But the purpose of showing this content today is that I believe robust optimization is a useful tool for giving us realistic optima while taking into consideration various engineering limits that we might come up against during operations. Now, it's very often that when we perform optimizations, we come to an optimal solution, but it's really walking the edge sometimes in terms of our system limits. So robust optimization is a technique for avoiding some of these problems by incorporating uncertainties in the system in order to avoid them leading us to some sort of failure of our system. So the presentation takes a slightly different format to a lot of the ones that we've seen today. It's it will come across a little bit more specific because I'm describing a particular project that we're working on and a particular case study. But the purpose is, I think, but I think it's a useful way to introduce this concept of robust optimization. So we all know the PS10 solar power plant depicted here. I believe this picture was taken in 2009 or so. As we can see, PS20 is still under construction. And we're going to use PS10 as a case study for looking into optimizing aim points of heliostats on the receiver. Now, what do I mean by aim points? Well, when we have a field of heliostats and pointing them to a receiver, we have the freedom of choice to choose how we point the heliostats to the receiver. So we have one extreme case on the left-hand side, which is when we point the heliostats all at the center. And in this case, we can expect that we might have a flux distribution that's very localized, but also very intense. And the receivers are not designed to accommodate this, or in particular, when we focus in this way, we see there's a lot of wasted receiver space there. And of course, if that were a feasible way to operate our power plant, then we wouldn't bother making our receivers that large. So the truth is that something like on the right-hand side is better. When we have a uniform flux distribution with a well-designed receiver, then we should find that flux distribution has a magnitude that corresponds to good operation, good heat transfer with good receiver efficiency. So, but as we can see, that also comes with the trade-off of potentially losing a bit of our flux to receiver intercept efficiency losses. So the state of the art in terms of flux distribution, aim point optimization, is summarized here in a table. We see it goes back all the way to the 80s with the Dellin citation at the top there, which was some heuristics for determining aim points within software package. And we have about 6 citations there that use anything from operational heuristics to simulation heuristics that attempt to optimize the aim point distribution. But I want to draw your attention in particular to the final citation there by Ashley et al. And excuse me, that's not too well conceived. So the final one there is the first one to approach this problem with a constrained optimization approach. And they use an integer programming algorithm in order to optimize the flux distribution on the receiver. And with this approach, we can begin to think about formulating the optimization problem in a way where we can ensure that we find the globally optimal solution. Now, Ashley didn't perform a robust optimization, which is the topic of this presentation. And as you can see, the current work is the first in the reviewed literature to implement a robustness approach in order to ensure a good flux distribution that honours the limits of the receiver. So our model is the PS10 heliostat field, and we have the tower here depicted with some important spatial variables such as the height and the size of the receiver there. And we simulate our receiver by dividing it up into bins with a finite amount of aim points. As you can see, there's 5 by 3 aim points in this formulation, and the bins there are our measurement points. So here we have the sun bouncing off the receiver and hitting our receiver here at one of these aim points, ideally. An optical model has been implemented that performs pre-computation of all of the different combinations, possible combinations of aim points for each heliostat, such to reduce computation time. And the optical model takes into account shading, blocking, cosine effect, and atmospheric attenuation, as you would expect. So with this model, we can begin by performing the non-robust optimization, which is very similar to what was done in the previous paper that I mentioned. And we perform this in order to make a comparison to our robust solution that we subsequently perform afterwards. So I don't need you to understand all the variables and the constraints that I've depicted here, but just to know that the top line is the objective function. So we want to maximize the amount of energy that we achieve at the receiver. But also we have a maximum flux distribution that we don't want to exceed. Now, usually for a reasonable flux distribution, we wouldn't exceed this anyway. But in order to demonstrate the utility of the robust approach, we've made this constraint a bit lower at 320 kilowatts per meter squared than what you would expect at the PS10 receiver. But the reason that we do this is because we always operate with fairly high safety margins. So this is essentially our, it's not our catastrophic failure value, but rather the value that we would like to allow ourselves to reach while still honouring or taking into account that safety margin. And we have another constraint here where we try to impose that the flux distribution is fairly uniform. So when we run our simulation, in this case, the optimization time is fairly quick. It's 4 seconds. We have an optimality gap of 0.41%, and what that means is that we can be sure to within 0.41% that this is the globally optimal solution. The receiver intercept that we achieve in this case is 59.1 megawatts thermal, and I should mention that the time of day is noon at summer solstice, and the solar irradiance was 1050 watts per meter squared. Now what we have here on the bottom left hand side is a representation of our receiver, and I apologize because I think the dimensions here are a bit different to what was in the first slide. But these are the dimensions that we used, and as you can see, the distribution on the receiver is fairly uniform, as you'd expect. But it's also quite close to our maximum flux that we imposed, which was 320 watts per meter squared. On the right-hand side, we have a field of heliostats, and this just shows how each heliostat points at the receiver, and it demonstrates that we've chosen carefully for each heliostat at which point in the receiver it should point. Now I think we have someone else on the screen there. Okay. Oh. Okay. Should I stop and see what he has to say, or? Okay. Okay. Good to see. All right. Now, here's where I start to talk about robust optimization. So the point is, with robust optimization is we define a sort of worst case. So if we have, as I said before, in the first slide where I showed the aim points, we have a kind of extreme example with this problem formulation, where if we point all of the receivers at the center, all of the heliostats at the center of the receiver, then we're going to get our biggest peak possible. And I'm just showing here a previous study where they used the PSA heliostat field, and they had a maximum flux distribution of 1300 kilowatts per meter squared. And they found that when they pointed all those heliostats at a certain design point in the center, that they exceeded that flux, and they thought, okay, that's the worst case. Let's make sure that even in the worst case, we don't exceed that maximum flux distribution, so that any optimal value that we come up with later is going to be sure to not exceed that. And so they switched off about 30% of the heliostats for that simulation. Now, this is an extreme case, because if you build heliostats, you want to use them. So switching them off in this way is not really a way that we would like to define our plant operation. So instead, we take into account the tracking errors, which is what could feasibly cause these peaks in flux distribution that might end up damaging our receiver or violating our safety margin. Tracking errors can cause unexpected peaks in flux distribution, and the previous aim point optimizations didn't account for this. So we take our formulation of our optimization that we had before, and we introduce into our safety parameter here, where we wanted to keep under our maximum flux distribution, an extra parameter. So just watching that again, we have our new term here, which is actually the result of a nested optimization. And in this nested optimization, it actually maximizes the heat flux at each point. So that's actually making the optimization, imposing it such that it makes a peak of flux, which is exactly what we're trying to avoid. But what we're doing is we're simulating the worst case, all right? And we have a subset of heliostats defined by this gamma parameter, which operate at the worst case. And we can choose that depending on how we think our heliostats are going to function. And what I mean by the worst case is the heliostats that subject to the limitations on the tracking area, which we chose to be 1 milliradian. In the worst case, for this subset of heliostats, they point in such a way that all of the fluxes from them constructively build and make the biggest possible flux spikes on the receiver. And by doing that, making sure that we still operate under our maximum flux distribution, we ensure that the aim points that we retrieve from the optimization, from the worst case optimization, will always be safe, because we've looked at the worst case in terms of the uncertainty. Now the results here look a little bit different from what I've shown before. So here again, we've got our receiver. Now the total, by imposing this robustness, the total receiver intercept has gone down by making this compromise. And we can see a little bit of, we can see on the receiver between adjacent points. I didn't realize that my mouse cursor wasn't showing on there. We can see that we've got a sort of alternating pattern here, where a subset of the heliostats have exhibited the worst case behavior by all pointing towards alternating bins on the receiver in order to provide constructive interference. And so, as I said before, this solution represents, the aim points that we get from this solution represent a safe mode of operation. Okay, and this time, I have to mention that this optimization was time limited. By introducing the nested optimization, we've really increased our computation time, and our optimality gap is 2.8%, and I know that's a lot in terms of receiver intercept. But nonetheless, we can already see the sort of qualitative solution or behavior in the solution that we would expect from a robust optimization. The receiver intercept here was 56.6 megawatts thermal in comparison to the non-robust solution of 59.1 megawatts thermal. So in conclusion, tracking errors can cause unexpected peaks in the flux distribution on the receiver. The calculated aim points provide a safe means for operation of the plant. And the robust optimization loses approximately 2.5 megawatts thermal, or 4.4% for a gamma of 5% of heliostats operating in the worst case. The robust optimization currently has a large optimality gap of 2.8%. So therefore, in future work, we would like to optimize the formulation of the optimization constraints in order to reduce computation time and get us closer towards that global robust optimal solution in order for comparison to current deterministic optimization approaches. And we would also subsequently like to generalize the formulation to allow for robust optimization of central receiver systems, which are of course much more topical these days. Here we see an optimization of aim points on a central receiver system that was performed using an optimization heuristic, and we'd like to extend that to include robustness and also to try to find the globally optimal solution. So I've gone a little bit under time, but I think that's okay given how we're going. So I'd like to thank you for your attention, and please, if you're interested in any of the references that I showed in the state of the art earlier, please look them up. Thank you.
Thank you very much also for the certain on time. Because so we have time for some questions.
This is admittedly a little bit off your topic where you're really looking at the ultimate flux on the receiver. But in the U.S., one of the big objections to solar power tower plants has been bird kill. And what they have found is the path that they take in bringing the receiver onto focus has an impact on that. It's those focal points out in space that birds seem to be especially susceptible to.
Okay.
Has there been any work that you're aware of that's looked at how you actually bring the tower on focus so that you can minimize this impact, environmental impact?
No, the short answer is no. But I do know that Cliff Ho of Sandia was doing some calculations on this. And my understanding was that he found that it wasn't too likely that birds would be killed by the heliostat, the flux distribution in the concentrations that we've been seeing. But maybe you can try and relate it a bit more to what I'm doing, because what we've done here is not model any sort of motion. We've found the ideal stationary points for the heliostats. If there were some sort of limit that could be identified in terms of like what kills a bird and what doesn't, or what hurts a bird and what doesn't, and you could, and you had some sort of uncertainty in your tracking paths, then you could use a robust optimization approach to make sure that you would never kill a bird, I guess, in theory. I wouldn't know how to formulate it at this point, but in theory, you could use that kind of approach.
Yeah, because you could have maybe a greater number of off-receiver focal points, perhaps each having a lower flux, maybe, I don't know.
Yeah.
If the problem is formulated properly, then I think that
yeah.
Sorry, that was one question, George.
Yeah, Jeff, I have a couple of questions from one of our online participants. One says, what flux safety factors are the receiver designed for, and what will be the consequences for a higher flux?
My understanding is that the safety factor for the PS10 is about 800 kilowatts per meter squared. And the consequences of exceeding that or getting particularly high flux spikes is a failure of operation. So you can reach your material limits, and you can damage the receiver, and that can turn into a runaway effect. So if you start to damage your receiver, then you can change the function of the receiver, and it can lead to problems. So I hope that answers the question.
Okay, one more.
Okay.
Wouldn't it be a better optimization by changing the focus point of the heliostat at various pins in the receiver?
I'm not sure I understand the question. Can you repeat it?
Says a better optimization can be changing the focus point of the heliostat at various pins in the receiver. Points maybe in the receiver.
Do they mean the focal length? The focal length of the heliostats? Because I'm changing the focal point. I mean, I'm changing the point at which you focus the receiver. If they mean changing the focal length, that would be specifically a design optimization in that case. And I think then you'd have to optimize for a lot of different cases in order to find the best design. I'm not sure. I think then you would have to do that for a sort of fixed aim point strategy, and then I think that aim point strategy is a lot easier to optimize for, because it's something that you can change during operation. So I hope that answers the question. I'm not sure I understood it completely.
Okay, thank you.
Okay.
Just a quick question. When you say 320 kilowatts per square meter,
Yes.
you mean it at the same density or flux density at a centimeter square, or is it an average over a square meter?
I mean that the optimization, the limit that the constraint that we put into the optimization had that as its limit at all points. So at all points that were in the optimization.
So if I go to a centimeter square, I get the same density, the same flux, right?
Yes. Yes.
Yeah, thank you. Which is the current situation of measurement equipment to see whether the flux that you predicted is the actual one?
We are a simulation group, so I'm sorry to have to give you that answer, but the work so far has been around formulation, and then we have our motivation is I would say that perhaps for your taste is theoretical, and so we're not really across the technology for measuring. So you're talking about measuring flux distributions at the receiver. I wonder whether there's a reason you asked that. Would you like to say something about it, or?
Well, we just said something. I think we continue that in the coffee.
Okay.
I think we wanted to get from you some idea of what is the status of the measurement devices, but this is an unfair question because it's not easy.
Let me ask a fair but simple one. Is your system prepared for dealing with mixed fields? I mean, fixed fields that consist of different type of heliostats, the good ones at the rear and the bad ones at in the center of the field, or I mean, different kind of error images and tracking errors.
Right. So that's a good question. So the formulation in its current form, are you talking about the quality of the error in tracking only, or optics as well? Okay. So we have a uniform optical error in this case, but I don't think it's a huge effort to impose a sort of known distribution of optical errors on that. In terms of the tracking error, the current formulation, as I said, it finds a given percentage. So you define a given percentage of the heliostats that have the maximum worst case error. And we're still thinking about whether that's analogous to a larger portion of heliostats having less than the worst case error. But you can see that there's a sort of general constraint, and But I don't think it's out of the question to just to define individual tracking errors and individual optical errors for each heliostat. I think it could increase computation time depending on the formulation you come up with. But I think it's very doable. Yeah.
We'll move to the next one, and if there are more questions, there were more questions. No. If there are more questions later in the coffee break. Thank you very much.
Okay.